Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be looking a little bit more at ice tables. And so we're going to be specifically bringing up stoichiometry. So one of the big tricks when we're working with stoichiometry is we're going to see a lot of our mathematical equations get increasingly complicated. However, we're going to respond by finding as many terms we can drop out as we can reasonably justify. So to introduce this idea, let's go ahead and kind of take an advanced version of what we did last time. So last time we looked at a simple isomerization reaction. 1 mole of reactant went to 1 mole of product. Now let's go ahead and look at another common type of reaction, a decomposition reaction. We've already addressed this one before. So the decomposition of dinitrogen tetroxide into nitric oxide. So this one is slightly reactant favored, so we won't expect it to proceed too much. So let's go ahead and try and figure out, well, exactly how much nitric oxide we'd end up generating. So let's go ahead and start by making an ice table for a starting sample of 0.2 molar nitric oxide inside an empty container. So this means we're going to start with all nitric oxide, dinitrogen tetroxide, no nitric oxide. So 0.2 molar and 0 molar. Now, the real difference starts happening here where we bring in change, because I'm still going to be consuming 1 mole of the dinitrogen tetroxide, but I'm going to be generating 2 moles of nitric oxide for every 1 mole consumed. Again, bringing in this stoichiometric ratio. So whenever you're looking at your change column, it should always be plus or minus x times whatever the stoichiometric coefficient is. 1 for the reactant, 2 for the product in this case. Then to get equilibrium, same process, we add together the first 2 rows. So 0.2 minus x and then 2x. Now that we have this, what we can do is plug these values into our equilibrium expression. However, we run into another difference here. Last time we didn't have any powers to raise any of our concentrations to. Here, note that our products are raised to the second power. So this means we have to raise that whole 2x term to the second power, meaning that we have 2 squared is 4, x squared is, well, x squared. However, the reactants are treated normally, no exponents. Now, in order to rearrange the system, we're always going to take our reactants and move it onto the left-hand side of the equation, combining it with our equilibrium constant. So here we can go ahead and distribute our equilibrium constant, and this will be the same as minus kcx and then plus 0.2, or our initial concentration, times kc. Then we're going to want to bring all of our x's onto one side, and we're going to set this equal to 0 because this should look familiar, because once we plug in our value, we have a good old-fashioned quadratic equation. And this is going to be very common with a lot of ice tables. So it's not going to be a bad idea to make sure you have your quadratic equation in your back pocket. So again, make sure you remember minus b plus or minus b squared minus 4ac all over 2a. Feel free to sing it. So here, our b value is going to be our 4.6 times 10 to the negative third. Our c value is going to be negative, which will make sure this whole inner part is positive. And then we have a value of 4 for our a, which helps simplify things out. So we go ahead and plug in all of these values, do the math, and we end up with an extended reaction of 0.015 molar. So we can then go ahead and plug this in to our ice table. We're going to decrease the concentration of our dinitrogen tetroxide and generate some nitric oxide in response. And one of the big things that is worth noting is if you actually add together all of the values, you will note that we have increased the total number of moles. If you add together these 2 values, you'll note that you have a greater than 0.2 molar solution. And this is very common because you are net generating products. If we had a 2 on the left-hand side, we'd expect to be net decreasing amount of species. So again, always pay attention whether your concentration should net increase or decrease by looking at the stoichiometric coefficients. So this isn't too bad, but again, it makes sense. We are mostly reactant favored, but you will always generate some products. In this case, not too much. However, it turns out that if we go to an even smaller equilibrium constant, even as the equations get more complex, we can make it a lot easier. So, for example, let's go ahead and look at the decomposition of hydrogen sulfide. So, hydrogen sulfide is that classic rotten egg smell. And it turns out it can decompose in air to make hydrogen and sulfur gas. Though, again, note, relatively unfavorable. And we're going to take advantage of this here because a times 10 to the negative 6 is about the point where we can start making things a little easier for ourselves, but very common sort of equilibrium constant to see. So what we're going to do is try and again build an ice table, and we're going to start again with a 0.2 molar solution. So we're going to place this into an empty container, set up our ice table, reactants on the left, products on the right. Do note that now we're generating two different product species. So my initial concentration for my reactants is 0.2, and both products we're going to assume none is already present. We're still going to be consuming our hydrogen sulfide, but now note we have a stoichiometric coefficient, so it will be -2. Stoichiometric coefficient on hydrogen, so it's going to be +2, and the sulfur is just plus x. So then we add together the previous columns, and it's 0.2 minus 2x, 2x, and x. So let's go ahead and use this to construct our equilibrium expression. This gets a little bit fun because note we have the 2x squared like we did previously, but we also have the x. So we have to distribute the square, solve for the x. However, the bit that I don't want to deal with is 0.2 minus 2x squared. That is going to be very ugly. However, we know that our equilibrium constant is fairly small, which means we won't be generating that much product. So the big assumption we're going to make here is that x is going to be small enough that 0.2 minus 2x is going to pretty much be 0.2. Let's assume that it doesn't change. Now, if we do this, we get really lucky because that whole bottom term now just becomes 0.2 squared. So that's 0.04. A lot nicer, a lot easier. Let's hope that it works. So we can go ahead and then solve for x. And note here that x is going to be 0.0035. With an initial concentration of 0.2, that is actually a pretty small value. So let's go ahead and plug it into our ice table. So let's plug in that 0.035, and we're going to notice we started with 0.2 molar hydrogen sulfide. We end with 0.193. Actually, that's fairly accurate. It didn't change that much. So adding in those extra mathematical terms will only improve this number a little bit. However, the big thing is that it does actually give us a pretty good idea of how much hydrogen and sulfur we're going to be generating. The answer isn't much, but depending on the sensitivity of chemicals you have, like sulfur can be quite aggravating to the senses, that may be sufficient to cause some issues. So this is one of the things we'll be often looking at is the examination of unfavorable reactions where small amounts of products can matter. This will become a major theme in next chapter. So again, what we're going to tend to see is the smaller our equilibrium value becomes, the more accurate this assumption. And it is worth noting there's going to be plenty of reactions that have equilibrium constants of 10 to the negative 30 that will still be quite relevant for chemistry. So this is going to be a fairly common phenomenon. So in general, if you're trying to evaluate whether or not you can drop that x on the quadratics or other terms, a good way to look at it is, does the change affects the sig figs on the initial? In this case, it does, but very barely. So this would be about the edge for where you can start making the approximation. So as we're going through different reaction families, I'll often tell you for that family where we can, where we should or shouldn't care about making this approximation, but definitely something to keep forward as we proceed. So this is what we do if we have a equilibrium constant that's very small. We can really help simplify our equations. We can also do a very similar thing if our equilibrium constant is really big. So let's say we're looking at nitrous oxide. So good old laughing gas, fairly common species. However, it turns out that it ends up decomposing into nitrogen and oxygen. So I want to know if I put nitrous oxide into a container, how much will I have left or how quickly will it decompose? So in order to do this, let's go ahead and take a look at this equilibrium constant. Whew, that's big. Nitrous oxide is not favorable at all. We're expected to break up quite sufficiently. So let's go ahead and try and build up an ice table, assuming that we have a initial pressure of 0.2 bar of nitrous oxide. So here's going to be the big thing. Since that equilibrium constant is going to be rather large, let's go ahead and start by assuming my initial concentrations and then saying, if I let this react, I'm really not going to have that much nitric oxide left. So let's say this reaction goes to completion. So if this reaction goes to completion, we have essentially 0 bar worth of nitric oxide left. And that's going to make it a lot easier to solve for x, because 0.2 minus 2x equals 0. Well, in that case, x is just going to be 0.1 bar. And then immediately lets us solve for the concentrations of the other two species. However, we already know there's going to be no such thing as a 0 concentration species whatsoever. So what we're going to do is take a look at this reaction, but now run it in reverse. So let's take those pressures we already had. So assuming the reaction went to completion, we know that we should start with, say, 0 nitric oxide, and then we made 1 bar of nitrogen and 1 bar of oxygen. Well, if we do this, then the reaction is going to run in reverse. We're going to generate nitric oxide, and we're going to consume N2 and O2. But this reaction is really favorable. So those X's are going to be really small. And so we're going to use the same idea we did last time. We're going to assume that our equilibrium concentration of our products is going to be the same as our initial concentration. That way we don't have to do any big fancy 0.1 minus x squared. Now what that lets us do is just then square our nitric oxide concentration. So that would become 4x squared. Ta-da! And now we can solve for x. So we can do this just like before. We're going to move the denominator over to the other side of the reaction. And this time it will switch place with our equilibrium constant. So then we take the square root of all of that. And we end up with a x value of 3.4 times 10 to the negative 7th. Yep, it turns out that was a safe approximation. 0.1 minus that value is 0.1, most definitely. On the other side, it actually does matter for figuring out how much nitric oxide would be left in the air. It would be about 6.8 times 10 to the negative 7th bar. Pretty much none. Now, there's two things I want to illustrate with this, is that, again, the same procedure we used for KCs does work for Ks or KPs as well. The second of which is that if I have a very favorable reaction like this, so for example, if I released a laughing gas into a room, and then I just let it sit, left it alone, let it react, because remember, equilibrium tells us nothing about how long it will exist. If I let it sit long enough, yeah, I'm pretty safe walking back in that room. All of the nitric oxide would have decomposed into nitrogen and oxygen, and we should be fine. So whenever you're looking at a equilibrium reaction, one of the 3 questions you should ask yourself is the reaction relatively 1-to-1? So look for a K somewhere between 10 to the negative 5th or 10 to the 5th, at which point you're going to have to do the hard math. However, if you have Ks much greater than 10 to the 5th or much less than 10 to the negative 5th, go for one of these cheat methods. Either assume the reaction goes to completion or assume that the reactant didn't get consumed at all. So identifying your scenario is going to be key to making ice tables simple. So next time, we're going to look at ways to try and figure out equilibrium constants for reactions you might not be able to look up the equilibrium constant for. So how can we rearrange equilibrium constants to get the value we need to complete our ice table? Until then, take care.